Hi students. So in the previous session, we derived the closed loop voltage gain and input resistance, output resistance and bandwidth with feedback for the voltage series feedback amplifier. Now, in this session, we'll consider voltage shunt feedback amplifier and we'll derive equation for the same four parameters. So, this is the configuration of the voltage shunt feedback amplifier. This acts as an inverting amplifier with feedback. So, you can observe that the input signal Vin is given to the inverting terminal and the non-inverting terminal is grounded directly, and this is the feedback path wherein the small amount of output signal is sampled back as the input to the op amp through the feedback resistance RF, and V in voltage is given to the inverting terminal through the resistance R1. And observe here, at this particular node V2, the current branches here. The incoming current, the current flowing through the R1 is I in, and this will branch out as IB, that is the input current to the base, and the current IF, that is the current through the feedback resistance. Since the input current to the op amp is equal to 0, or it is negligible, so we will make it almost equal to 0. So the same current that is flowing through R1 will flow through resistor RF also, and this op amp will amplify the input signal no doubt in that. So the output signal's amplitude will be very much greater than the input signal. So as and when there is an increase in the output signal, since there is a feedback, the output signal is fed back to the input terminal, this will cause the decreasing in the output signal. So this arrangement forms the negative feedback, and the direction of current is from the input side to the output side. So next we'll proceed with the closed loop voltage gain derivation. First, what we have done is we'll apply KCL at the node V2. So we'll apply KCL at the node V2. As I told you earlier, the current branches out at this terminal. Since IB is very small, we'll almost consider it to be 0. Therefore, IN will be equal to IF. So here In is equal to IF plus IP. Since IB is equal to 0, IN is almost equal to IF. And now what I'll do is I'll write the equation for IN. I'll write the equation for IN as Vin minus V2 by R1. And what is the equation for IF? That is the current through the feedback resistance RF. V2 minus the voltage at this terminal is V0 divided by RF. So I have written this and I've named this as equation 1, and this op amp will amplify the difference in the output signal. So the input signal, sorry, the output voltage will be equal to the difference in the input signals, and the multiplied with the open loop gain of the amplifier. So from this equation we can write the differential voltage V1 minus V2 as equal to V0 by A, isn't it? So now, since this V1 is equal to 0, since the voltage at terminal at node V1 is equal to 0 because it is grounded, I will write V2, I'll just substitute V1 is equal to 0 in this equation, and I'll get V2 is equal to minus V0 by A, and I'll name this as equation 2. So now I'll substitute this in equation 1. So I've substituted here, and upon simplification I'll get the closed loop voltage gain as equal to minus ARF by R1 plus RF plus AR1. So this is the exact value of the closed loop voltage gain, and I'll name this as equation 3. And you can observe that here we have got the negative sign. This is because this indicates that there is phase shift between the input signal and the output signal, meaning both the signals are out of phase because it is inverting amplifier. And now here in the denominator, observe you have A into R1. Now we know that open loop gain of an op amp is the ideal value of it is infinite. So A into R1 plus R1 plus RF. This R1 plus RF is very small when compared to A into R1. So I'll just write A into R1 instead of this big term. So AF will be equal to minus A RF by A R1. A and A will get cancelled in the numerator and the denominator, and the remaining will be minus RF by R1. This is the ideal equation for closed loop voltage gain of the inverting amplifier, and I name this as equation 4. So now here I need to express AF in terms of the open loop gain A, as we did for non-inverting amplifier. The same we'll do for inverting amplifier as well. What did we do there? We divided both numerator and denominator by the term R1 plus RF. So here also I'll divide both numerator and denominator by R1 plus RF. Okay, so whatever I have written in the red pen is the changes that I am going to make in this equation. And here R1 plus RF, this denominator term is broken up into two parts, two terms. Okay, R1 plus RF will form one term and AR1 alone will form the other term. And here if I divide by R1 plus RF, this term will be reduced to 1, and here R1 divided by R1 plus RF is equal to the feedback gain of the feedback circuit, and here RF by R1 plus RF is the voltage attenuation factor. Okay, so that is indicated by the letter K. Okay, so I'll write minus AK divided by 1 plus AP. So name this as equation 5. This is very important. And this is the one line diagram of the inverting amplifier with feedback, wherein we have used voltage summing junction. Here as you can see, input voltage is V in, and it is attenuated by a factor K, and here this is the feedback network, and here V naught, meaning the output voltage, is given as the input to the feedback network, and the input voltage will be V naught for the feedback factor, the feedback circuit, and the output voltage will be VF. And since this is the negative feedback, minus sign here, and this difference V in minus VF is a differential input voltage VID, and it is given to the op amp, and the output voltage after sampling it to the op amp through the feedback network will be V naught. And here consider the equation 5 here. Now we got AF as equal to minus AK by 1 plus AP. Now we know A is very large, so A into B will be very much greater than 1. So 1 plus AB, I'll write it as just AB. So AF will be equal to minus AK by AB. A and A will get cancelled in the numerator and the denominator, and substitute the value of K and B as RF by R1 plus RF for K, and R1 by R1 plus RF for B, and the resulting gain with feedback will be equal to minus RF by R1 because it is a inverting amplifier. Now the next topic is inverting input terminal at virtual ground. Now by the concept of virtual ground, what we understood is the voltage at the inverting terminal and the voltage at the non-inverting terminal, they both are equal. So now what we do is, see, here V1 is grounded but V2 is not grounded. Vin is given to V2, but for further simplification we'll consider the concept of virtual ground, and we'll say that the voltage at inverting terminal V2 is also at ground potential, and we'll write V1 is equal to V2 is equal to 0. So we know that since the input current to the op amp is equal to 0, In is equal to If, and we wrote this already. And here now I'll apply this concept, virtual ground concept, and V1 is equal to V2 is equal to 0. So I'll substitute the value of V1 and V2 here in this equation, and I'll get V in by R1 is equal to minus V0 by RF, and I'll get AF is equal to minus RF by R1 because it is a inverting amplifier.